All right, our final speaker for this session is Don Goldfarb, who's going to be talking about fast first-order methods for stable principal component pursuit. Thank you.
Thank you. I want to thank Rebecca and everybody else at Duke who organized this meeting. It's a great meeting so far. It's about to go downhill. But until now, it's been great. Anyway, I'm also very pleased to be in this session because the two talks before mine cover a lot of the material that I'm going to talk about. So I'm talking about the problem of, specifically the problem of stable principal component pursuit. That's the, which you saw an example of, which, sure. Which Rick talked about, of decomposing a video into the foreground and the background. That is the moving foreground and the background. And that's called the robust principal component pursuit problem. And then at the very end, he even discussed the problem that I'm talking about, which is the stable one, where you're also interested when there is additional noise that let's say is Gaussian. So we'll switch right away to the convex relaxation of the problem. Instead of minimizing the rank of x plus some multiple of the number of non-zeros in the S, which is supposed to have a few, mostly zero elements, there's noise in the data matrix D. So D is this matrix that has a low-rank part, a sparse part, and noise as well. Okay, and the convex relaxation of that people address, although Rick talked about a non-convex version of it, is replacing the rank by the nuclear norm, replacing the cardinality of S by the vector 1 norm, that is the number of non-zeros, in the problem. Okay, so it has many applications, and you saw this video surveillance or video decomposition problem. Of course, special cases of it are the low-rank matrix completion problem. That's where C, or the sparse term, doesn't exist. It's only the low-rank term. And, it's well known that that problem, if certain conditions hold, that you, with very high probability, by solving this convex problem, you get back the solution to the, in general, NP-hard problem of finding the minimum rank solution with a subset of entries known. The robust principal component pursuit problem is the problem listed there, where you want to, where you have no noise, and there the, it was shown that if the data matrix can be written as a low rank plus a sparse part, and the rank is small enough and the number of non-zeros is small enough, then with very high probability, you get a solution, you exactly recover the X bar and the S bar by solving this convex problem. That's a result due to, I guess, was proved in I guess, Lee, Ma, Candace, and Wright. Not necessarily in that, I mean, I don't have the order of the authors in the paper, right, but those are the authors. They also, those same authors then prove that for the stable principal component pursuit problem, will recover, you can't recover the exact solution, but as you can see in this slide, that if the original data matrix was made up of a low-rank part, a sparse part, and noise, and that noise in Frobenius norm was less than delta, that with high probability, and the rank is small enough and the number of non-zeros is small enough in the sparse part, that with high probability you recover a solution X star S star that satisfies this inequality in the next to the bottom line. That is, it's as good as you probably can get, considering that you have noise. Okay, and that was also proved by the same set of authors with a fifth author named Joe. And so this is a thing you can, a particular video you can find in their paper, different from the one that was shown to us by Chartrand. The bottom one shows a completely, there are many frames. This is just one frame in this video. Unfortunately, I don't have any moving video. I just have a single frame here. That frame at the bottom line is the original frame. When you apply the methods I'm going to talk about, you recover the background, which is the bottom row, second image, and the foreground, which involves the people who are moving through the video on the right. And as you may notice, there is a person that somehow gets in the background because that guy is just not moving through this whole sequence of frames. And then as you go up a row or up to the first row, just increasing noise. So in the top row, you have a very noisy video, and what you recover is, again, shown in the right two columns. Okay, you get the foreground and the background. The background comes out fairly noiseless, but the foreground has noise plus the Gaussian noise plus the moving foreground. So, no one else has mentioned this thus far, but that problem of this stable principal component pursuit problem is solvable in polynomial time because it can be formulated as an SDP. And in fact, the bottom half of the screen there shows the SDP formulation. You can solve SDPs by interior point methods in polynomial time, but it's pretty useless to solve by today's methodologies for solving interior point methods. For interior point methods, to solve an SDP that has much more than, let's say, 200 by 200, a matrix that's bigger than 200 by 200, if you have a reasonable number of constraints, some fraction of the reasonable fraction of the number of entries in the matrix. And that particular video problem that I showed you on the last slide has about 25,000 pixels per frame, and there are, I think, 200 frames. Consequently, it's not 25,000, but it's the number of rows and columns in that semi-definite matrix with W1 and W2 and X transpose and X. That matrix would have 25,200 rows and columns. And so it's way beyond the range of interior point solvers. Can't be solved. The only algorithm I know that's specialized specifically, and of course we've learned about some new algorithms here today, but the only ones I knew about when I wrote up the slides for solving this problem is an alternating splitting augmented augmented Lagrangian method due to tau and yuan. That problem, that algorithm looks at the augmented Lagrangian of the problem nuclear norm of x plus c times the 1 norm of s, subject to the constraint x plus s plus z equals d, and Frobenius norm z less than delta. It generates infeasible iterates, but has been shown to be convergent. However, there's no complexity analysis of the algorithm. And so what I was interested in when I got into this problem, and I started talking to this student, Serhat Abot, was could you take some of the well-known first-order algorithms that have complexity bounds and apply them to this problem and do it in a way that each iteration of those algorithms was cheap. In other words, those algorithms are, they find an epsilon optimal solution in something like order 1 over epsilon iterations. But if the iterations are not easy to do, it's not going to be any good. Okay? So the question is, can we apply those algorithms, and can the subproblems that have to be solved at each iteration be done efficiently? And that's really the purpose of what I'm going to talk about. So there are a whole bunch of algorithms. There's Nesterov's fast gradient algorithm, which can be applied to both sum of two functions where the functions are both smooth, and there's a constraint set that's fairly simple. Usually, that usually means a constraint set like the non-negative orthant. Then Nesterov has another method he calls, I think, gradient method for composite objective functions, where only one of the functions has to be smooth, that is, have a Lipschitz continuous gradient, and the other one, they both have to be convex, but the other one can be non-smooth. And another one, a related algorithm, is the algorithm due to Beck and Taboul, where there's a fast version of it called FISTA. So the algorithm due to Nesterov is given there. FISTA is a little simpler looking, but they both end up dealing with a function which is P in this case, which is convex and non-smooth, and they linearize the smooth function f. So you evaluate f at the point xk, and you have this gradient term, and then you have a Prox term, okay? And so if you look at, if you apply this algorithm, it's proved in these papers that you get a solution to the problem in something like square root of L over epsilon, where L is the Lipschitz constant on the gradient f, iterations. You get an epsilon optimal solution. Now, in the problem we're talking about, actually, before I get to that, in the problem we're talking about, both functions are non-smooth, because one is the nuclear norm, and the other function is the one norm. So they're both not smooth. So you have to, there is no algorithm that will deal with two non-smooth functions and give you a complexity analysis. So the two algorithms I just talked about have this nice complexity if at least one of the functions is smooth, or if both of them are. So you can smooth the f is the function there is the nuclear norm. You can smooth that by replacing it by the function I just wrote there, and the g function, which is the one norm, can be also smooth as shown in the second line. And then the various algorithms I was talking about, the smooth Nesterov, where both things are smooth, you have to solve the bin of the smooth f and the smooth g subject to x plus s being in the set chi. Chi is the set such that x plus s minus d Frobenius norm is less than sigma. It's the noise, okay? And because you have to do smoothing, the L, the Lipschitz constant, turns out has to be something like 1 over epsilon, so the total complexity is 1 over epsilon. The FISTA algorithm, you see that you only have to smooth the, let's say, the nuclear norm term, and you leave the one norm term alone. And then there's a whole set of algorithms that I've developed based on alternate linearization, where you alternately minimize respect to the x variable and then the s variable, and you do splitting. You introduce a new variable. So here we introduce a new variable. We set x equals z, so that when we do the minimization over x, there's no constraint, but when we minimize it over s, there is a constraint. S and z, there is a constraint in those problems. and it also has the same complexity. But the real issue is, what about solving the subproblems? So it turns out, when I minimize in the first algorithm, Nesterov, I have to minimize, I linearize both f and g. Okay? So there's no other terms there. When I do the Pfister algorithm or the FALM algorithm, I end up, when I minimize with respect to s, I have the one norm. Okay? So in the first algorithm, I have to minimize something that looks like the Frobenius norm squared of s minus s tilde and x minus x tilde squared, subject to x and s lying in this constraint set. And the constraint set is given there on the first line. Okay? In the problems, in the other two algorithms, I only have to minimize problems, the only difficult problems that I have to consider are the problems that look like minimizing the one norm plus a quadratic term subject to a ball constraint, okay? And the other thing I have to minimize is just a linear system like Mario was talking about, where I end up with linear systems that I have to solve. I'm not going to deal with that because we all know how to solve those. In any case, what we realized at first, we didn't realize that these were easy problems to solve, but in fact you can show that they are easy to solve. The first one, turns out you're really projecting in a Euclidean sense onto this ball, and it's that subproblem listed on the first line there, and you can write down explicitly what the answer is. Okay? The second problem, when you want to minimize the one norm of s plus some x minus x tilde squared, subject to x plus s minus d norm squared less than sigma squared, that also turns out to be easy to solve. And if you go through the analysis, you can show that it can be solved by a shrinkage operation, followed a shrinkage operation which involves a term theta star, where theta star is the solution of a fourth order polynomial. Okay? You actually have to solve a fourth order polynomial, but that can all be done efficiently. So it turns out that you can solve all of this in O of mn log mn time. So that's the work per iteration. To do the to actually do and that's trivial compared to the part where you have to do an SVD of the to compute the update of the x variables. Okay, so the point is that up until this point, I've developed a bunch of methods that you can use to solve these problems and actually give nice complexity results in terms of both iterations and the amount of work it takes per iteration. We then looked at, and they work reasonably well, but it turns out, as is often the case, the method that works the best, you don't have the best theory for. And the method that actually works the best is the following. We again split the variable x, and we introduce a new variable z, and we let x equal z. And so instead of solving the problem just in terms of x and s, we minimize that objective function subject to x equals z. And now instead of having x in the constraint, we have a constraint that says z plus s minus d in Frobenius norm is less than sigma. So now we have no x in the constraint. Then when you, in your algorithm, and you do alternating direction method, a la Mario's talk, you minimize the augmented Lagrangian, but only we're doing an augmented Lagrangian with respect to this equality constraint. The inequality constraint, the chi constraint, is kept separate. So we minimize the augmented Lagrangian in an alternating way. First, we do it with respect to x, right? Subject to the constraint, but now x is not in any constraint. Okay? Because I've taken x out of the constraint by setting x equals z. So that's just a unconstrained minimization problem when I do the augmented Lagrangian, right? It's just a, okay, and that's going to be solved by doing an SVD and shrinkage on the singular values. Then when I minimize with respect to the other variables, but now there are two sets of variables, z and s, I do the same augmented Lagrangian. Okay, you know, I don't have in there, in the first one, I don't have the s because it's fixed in the first line. Okay? Now when I minimize the augmented Lagrangian with respect to z and s, I drop out the x term because it's constant, and I minimize cs, you know, the one norm of s plus this Lagrange multiplier yk times xk minus z, and I'm using the most recent value of x that I got from line 2, okay, because I'm now computing sk plus 1 and zk plus 1, plus the, you know, the penalty term, subject to zs in the constraint. Well, we know how to solve that problem because it's exactly one of those problems I talked about before. It can be solved efficiently. And then we update the Lagrange multipliers, as is typical in the augmented Lagrangian method. And we also have the flexibility of increasing the penalty parameter from one iteration to the next. And all that theory is well known. But this is not standard alternating direction augmented Lagrangian algorithm. And therefore, one needs to show that it actually converges, and it does. You can show that if you apply that algorithm and the sequence of rho k values, these penalty parameters, are such that the sum of their reciprocals is infinite, you get convergence to the optimal solution. And in fact, if the second line is true, that is the sum of the reciprocals squared is infinite, essentially you get that the Lagrange multipliers go to this Lagrange multiplier vector goes to the optimal Lagrange multiplier. Okay? Quickly, we create rank R matrices by randomly creating a U matrix and a V transpose, multiply them together. We randomly generate a sparse matrix S, you know, with Gaussian entries and randomly chosen indices, and we add Gaussian noise, and we look at problems that are 500 by 500 up to 2,000 by 2,000 with, you know, 5% of the columns are, you know, with rank equal to 5% of the dimension to 10%, and sparsity parameter 5% of the entries are non-zero to 10% with noise that's 10 to the minus 3, and we compare our algorithm. I mean, you can show that our algorithm across these various parameters typically takes about 12 or 13 iterations. That's the number of SVDs we have to compute. And those are the times in CPU seconds. I don't even know what we did it on. I think a laptop. And we get very high solution accuracy, relative solution accuracy. And just to show you how nicely the results come out, this is a 1500 by 1500 matrix. That happens to be one row of the matrix. That's the sparse part of one row of the matrix. The elements are either positive or negative. They run between 100 and minus 100. The next line shows the solution. The next line shows the difference in the true solution from the you know, the true value of S from these are the sparse components from the one we compute, and you can see that it's of order like 10 to the minus 3. It's very small, the error being the difference. And on the right are the original singular values of the matrix X, and the blues are the computed ones. And this is just another with more noise, okay? Similar kind of results. When we compared our algorithm to this ASLM algorithm, the number of SVDs are typically less than half those required by the other algorithm. And if you look at the time required, it's between 100 and 200 times faster. I'm about to done. And then this is the video surveillance thing, which I don't have to spend any time on. That's when it's applied to a no noise case. Those are now 3 different frames across the top, and the decompositions now go row 2 is the X variables, row 3 is the foreground, the moving foreground, and that's the slide I showed you before. And the paper is available. It's been posted in archive. It's ABOT, Goldfarb, and Iyengar. Thank you.
Thanks very much. Are there any questions?
So Don, how do you know the noise variance?
Approximate, yeah.
How sensitive is it to noise?
I don't really know. We've never tried it. You know, I would imagine that if you have that wrong and you are underestimating it, it would be like solving, you know, taking a noisy video and doing robust PCA on it, assuming that you're getting an exact image. I would think that you'd get okay, depending upon, as long as it's not too far off, but it could deteriorate. I would imagine, but I have no idea. I mean, I've not tried it. I'll try it. That's an easy thing to try. Anything else?
Yes, Zach.
So just in the outline of your algorithm, you talk about flexibility increasing the augmented Lagrangian parameter, but you didn't really talk about how exactly.
How did we do that? I mean, that's a standard. It's not. It's the penalty term. So, for people who do nonlinear programming, and I'm an optimizer, and you know, for years people who used augmented Lagrangians, the way one typically does that is one keeps that penalty parameter. The whole idea of augmented Lagrangians versus penalty methods is that in penalty methods you have to let that parameter go to infinity to get a solution. In augmented Lagrangians, there's a fixed number. If you make it large enough, then the solution is you'll get the solution to the constrained problem. So in our problems, we had x equals z.